So in this video, I'm going to show you how to calculate the specific volume for a given pressure and temperature using the cubic polynomial that we derived in part 2 and Cardano's equation to find the roots of that cubic polynomial. So a little bit about Cardano's equation is it is essentially the quadratic formula, but for cubic equations. So it finds the root of cubic equations. So here on the left side of the screen, I have the steps for Cardano's formula, and we are going to read through this as we code and code this formula into our as a function in our Python code. So I'm going to create the function. I'll just call it cube roots, and we need to pass it the coefficients a, b, and c. Right? And now our next step is, so with real or complex coefficients, we have all real coefficients. We need to first compute q, which is a squared minus 3 times b divided by 9. And we need to compute r. So r is just going to be 2 times a cubed minus 9 times a times b plus 27 times c, all divided by 54. Right? So now if we keep reading through this, so if q and r are real, which is always true when a, b, and c are real, so our q and r are going to be real since we have real coefficients. And if r squared is greater than q cubed, then the equation will have 3 roots. So we'll put this in. So if r squared is less than q cubed, we're going to have 3 roots, and we calculate those roots by first calculating theta, which is the arc cosine of r divided by q to the 1.5 power, because over here we have q cubed, and then we take the square root of that, and that is the equivalent of q to the 1.5, or 3 over 2. Then we can calculate our roots. Our roots will be -2 times q to the 0.5 times, and if you notice, they all have the exact same form, except they have a different value in their cosine, in the cosine. So I'm going to code essentially like the outer part of the function, or of the root equation, and then inside cosine I'll use an array to put these 3 values, right? So we'll have cosine, and now I'm going to use an numpy array, and our first value is theta divided by 3. Our second value will be theta plus 2 times pi over 3. And our third value will be theta minus 2 times pi over 3. And then this whole thing will subtract a over 3 from. So there's our a over 3. So from there, before we return these first 3 roots, we are going to sort them. So this will sort, this function, numpy sort, will sort them in ascending order, so from lowest to highest value, and it'll kind of make it easier to use in our code later on. So now, if we keep reading, we're not quite done with Cardano's formula. If r squared is not less than q cubed, we only have one root, one real root, and it's calculated using this, a plus b minus a over 3, where a is this equation and b is two values depending on the value of a, right? So in our else, we first need to calculate a, which will be equal to the sine of r, which this sine function, when given a positive value, returns positive 1, and when given a negative value, it will return negative 1. And so the negative sine of r is multiplied by this set of brackets, all to the 1/3 power. And in the brackets, we have r plus the square root of r squared minus q cubed. And now, if a is equal to 0, then b will also be equal to 0. And if a is not equal to 0, b is calculated using q over a. So we will now, we're going to code this using a ternary if. So it's basically, it's kind of like a shorthand if, and it allows us to write this all in one line. So b will be equal to 0 if a equals 0, else it will be q over a. And now we just need to return the root. So we calculate the root using a plus b minus a divided by 3. And there is our cube root function. So now we actually need to solve our cubic polynomial and calculate the specific pressures, or not the specific pressures, the specific volume. So we're going to do that by creating another function, and I will call it SRK, since we're using the SRK equation, sub specific volume, right? And we're passing a temperature and a pressure to this function because we are calculating the specific volumes at a set temperature and pressure. So we need to use our cube root function that we just coded and pass it the a, b, and c values, or the a, b, and c coefficients for that cubic polynomial from part 2. So here are the coefficients. Our z squared will be a coefficient, this will be our b coefficient, and this will be our c. So now we're going to code this into our cube root function. A is going to be epsilon plus sigma times beta minus 1. B is going to be epsilon times sigma times beta squared minus epsilon plus sigma times beta cubed, or beta squared, minus epsilon plus sigma times beta plus q times beta. And now for the c coefficient, it will be negative epsilon times sigma times beta cubed minus epsilon times sigma times beta squared minus q times beta squared. There we go. And this will be our z roots. So now, obviously, we're missing quite a few values. We're missing epsilon and sigma, and beta and q. So we'll calculate epsilon and sigma using this function up here that we wrote earlier, using our SRK ABS function. And then we also need to calculate beta and sigma. So we come back to our thermodynamics equations. Beta is equal to B times the pressure over R times T. And Q is equal to A divided by B times R times T. There we have it. So now we have our z roots. From here, we know the relationship between our specific volume and z, and we can calculate our specific volume. So Z, which is the compressibility factor, is equal to the pressure times the volume divided by RT. So if we rearrange this equation, we will get the specific volume equals R times temperature times compressibility Z, all divided by the pressure. So that's our roots. We just need to return them. And since we already sorted our roots of Z in the cube root function, they'll come out and be sorted as well in this one. So now let's see if it works. So SRKV will have a temperature of 500, and let's say the pressure is 1 atmosphere. It looks like I have an issue in. Alright, so now I had the error in my code sorted out. I had an issue just typing in the equation for the roots right here. Now that that's solved, let's run the code and see if we get the correct values, right? So I'll just run it at, again, 500 Kelvin and 1 atmosphere for the pressure, and there we get our 3 roots. So this first root is the specific volume for the liquid. This middle one is just the non-existent volume that is under the liquid vapor phase envelope, and this is the specific volume for our vapor.